This begins a pre-lab introduction to Lab 4 called Systems in Equilibrium and Le Chatelier's Principle. We've not yet discussed Le Chatelier's Principle, and I wanted to take an opportunity to be sure that you had a sound foundation for the lab today. So we're going to be talking about disturbing a chemical equilibrium. We know that when reactants, such as reactant A and reactant B, form a dynamic equilibrium, we can call that products C and D. We know that the rate of the forward reaction is equal to the rate of the reverse reaction. That's what's known as dynamic equilibrium. This particular lab says, what happens if we upset an established equilibrium by applying a stress? There are three different types of stresses that will affect and shift equilibriums. Changing the temperature, changing the concentration of a reactant or product, or by changing the volume and thus affecting the pressure for systems involving gaseous forms. So I'm going to talk about each of these one at a time and then apply it to the systems that you'll be studying in today's lab. Le Chatelier's principle defined, and as you've read through your pre-lab, it says a change in any of those factors being change in concentration, change in temperature, or change in pressure, will cause the system at equilibrium to shift back towards the state of equilibrium. In other words, whatever you do to upset a system, the system counteracts that by doing the opposite. If you add more of a reactant, the system wants to use the excess amount and get back to the established value. Let's take a look at that closer, the addition or removal of a reactant or product. We know if the concentration of a reactant or product is changed from its equilibrium value at any stated given temperature, equilibrium goes back to be reestablished eventually. Over time, the excess amount gets used up. The new equilibrium concentrations will be different, but remember the new established constant, K, will remain the same. Let's take a closer look at what that means, changing concentration, and I'm going to use a sapling example to modify this, to example it. Let's consider the following equilibrium. I have 2 units of carbon monoxide reacting with 1 unit of gaseous oxygen, forming 2 carbon dioxide molecules. This is in a dynamic equal state to where we know the equilibrium constant would be expressed as the concentration of the carbon dioxide squared over the concentration of carbon monoxide squared times the oxygen. Products over reactants, the coefficients become the power with which they're raised. This K is indeed a constant as long as the temperature does not change. So what happens if we change the concentration of one of these ingredients? What will the reaction do to reestablish itself and get the K constant back? Let's suppose, for example, we increase the concentration of CO. The notation used for that is an up arrow to represent an increase in concentration of CO. That upsets the equilibrium. If we increase the CO, K is no longer constant. The others have to adjust. By adjust, I mean they have to reestablish values to get K back to be the same number. So if I increase CO, what's the opposite of that? The opposite of more is less. We want to use up the excess amount of CO. To use up a reactant, we point away from it. By pointing away, reactants get used and products get made. This reaction will shift to the right by increasing the concentration of the reactant CO. That would be true as well if we increase the concentration of oxygen. The reaction would also shift right to alleviate the excess amounts and reestablish equilibrium. What if, as in letter B, it says, what if we increase the concentration of carbon dioxide? So this is the initial stress. Let's increase CO2. And again, here we're increasing the amount of product. That disturbs an equilibrium. The opposite of more is less. You want to use up the excess amount, so you point away from it. Using up the excess amount will make more CO and O2. This reaction will shift to the left. Le Chatelier's principle. By disturbing the equilibrium by changing either the concentration of reactant or product, forces the equilibrium to shift to reestablish the initial state of equilibrium. Let's consider this example from your sapling problems. We have solid sulfur reacting with gaseous oxygen in dynamic equilibrium with sulfur dioxide. Now remember, this equilibrium says that the concentration of SO2, which is in a gaseous form, set over the concentration of oxygen, all raised to the first power, but we have learned to eliminate pure solids or pure liquids from an equilibrium reaction, from the equilibrium state. So pure solids, pure liquids do not get included in our equilibrium expression. So if we add more solid sulfur, the solid still just sits at the bottom of the equation, the bottom of the beaker, doesn't partake in any more reaction. There's actually no effect because pure solids or pure liquids do not play a role in shifting equilibrium. So never think about solids or liquids in Le Chatelier's shifting. What if we remove some of the sulfur dioxide? And we would denote that by lowering its amount. If we remove some sulfur dioxide, and you could do so through a competing reaction, introduce another chemical into the container to consume the SO2, well, the system will counteract by wanting to make more SO2. If you take some away, it wants to make more so that the K becomes the original value. And by doing that, to make more, you have to point at it. You're going to shift that equation right to make more of the SO2. Whatever you do to the system does the opposite to counteract and get back to the established state. A second type of equilibrium disturbance is the effect of changes on gas phase equilibrium. We're going to change volume and therefore change pressure. So if we have reactions involving gases, what happens to the equilibrium concentrations or pressures of the system if the size of the container is changed? And here we have to bring back what's called Boyle's law. We know that pressure and volume are inversely related. If I have a container that's sealed, such as a piston or a syringe that is capped, and I have a certain number of gas molecules, and I decrease the volume in which they're contained, decreasing volume increases pressure. Boyle's law says they have an inverse relationship. So inversely related, we know that PV is PV. So that's from our gas laws instructions in first semester. Now, how do we manipulate pressure changes in a system? Well, we do so by changing the volume of the container the molecules are held in. If we decrease volume, we increase pressure. And the system wants to reestablish the equilibrium, so it wants to favor the side with the fewest gaseous particles to drop the pressure. Now remember, collisions is the definition of pressure. If I have a system with a lot of gaseous molecules, that's high pressure. If I want to have lower pressure, I want to create fewer molecules in our dynamic equilibrium. Let's take a closer look at an example with one from your homework. It says, consider the following system at equilibrium. 2 units of CO as a gas react with gaseous oxygen to form 2 units of CO2. Notice how there's a total of 3 gaseous moles on the left and 2 gaseous moles on the right. 3 moles recombine to form 2 moles of carbon dioxide. If we decrease the volume, we increase the pressure. So the stress is increasing pressure. Remember that inverse relationship. And if this is the stress, what will the system want to do to counteract it? To counteract high pressure, we want to lower the pressure. And which side of that arrow would lower the pressure? To drop the pressure, we need the fewest molecules. Fewer molecules make fewer collisions, and the side with fewer molecules is the product side, carbon dioxide. If we decrease the volume and therefore raise the pressure, The system will counteract by favoring the side with fewest collisions, which is the product side. It'll shift to the right. Notice here we have a system at equilibrium where we have a solid sulfur reacting with gaseous oxygen, producing sulfur dioxide. We understand that pure solids and pure liquids do not play a role in the expression of equilibrium. So therefore, on this particular side, the left side of the arrow, there's one gaseous mole. And on the right side of the arrow, there's one gaseous mole. Because they are the same on both sides, changing the size of the container will not affect the overall pressure of the system. So decreasing volume will increase the pressure, but it won't shift the equilibrium either way because there's the same number of molecules on both sides. So here's a special case where when there are the same number of gaseous moles, changing the size of the container does not shift the equilibrium. So in conclusion here, changing volume changes pressure with an inverse relationship according to Boyle's law. Increasing the volume favors the side with the greatest number of gas particles. In other words, if we increase volume, we've dropped pressure. What will the system do if the stress is dropping pressure? The system wants to create higher pressure, and that means more molecules. Greatest number of gas moles will be favored. The opposite is true here. If you decrease the volume, you've raised the pressure. That's the stress. So therefore, the system wants to drop the pressure, and therefore the fewest number of moles will be favored. And when they're exactly the same on both sides, we saw that there's no effect by changing volume and thus pressure. So far, we've talked about concentration as a stress. We've talked about pressure and volume relationships. Let's take a peek at the next, and that would be changing temperatures. Now remember, equilibrium constants are temperature dependent. So changing the temperature does indeed change the value of the K constant. Let's think about exothermic reactions. Let's suppose we have A plus B in dynamic equilibrium with C and D, and it's exothermic, so we know delta H is a negative value. Let's just make up a number and say it's negative 100 kJs per mole, exothermic, heat releasing. I want you to think about that as just another product coming out on the right side of the equation. Releasing heat means it's coming out of the reaction. It's a product. Just like C is coming out as a product, D is coming out of the reaction as a product, and so is heat. Now this becomes very simplistic in terms of stress. Let's suppose you increase the temperature of the reaction. If you increase the temperature, there's the stress arrow. What's the opposite of more heat? Well, it's less heat. You want to move away from the arrow to use it up. This reaction will shift left. In an exothermic reaction, heating it up shifts the reaction left to make more of the reactant. What if it's exothermic and you cool it down? If you cool the temperature, the reaction says, well, I want to do the opposite of less heat. I want to make more heat. That would make the reaction shift to the right. Thinking of exothermic reactions, place the heat content on the product side and then treat it just as you would for the concentration changes. Let's suppose we have a reaction where A plus B is in dynamic equilibrium with C and D, but it's endothermic. So delta H comes out to be positive, and let's just for the sake make up a number, 100 kJs. Endothermic means heat must be placed into the reaction to cause it to start. So I'm going to place it over here as a reactant. Just as I have to put in reactant A, I have to put in reactant B, I have to input heat to force the reaction to go. Now it just becomes as similar as the concentration units. If you increase heat of an endothermic, it shifts away from it, forming more product. If you decrease heat of an endothermic reaction, it will shift left to make more heat. Treating exothermic heat as a product, treating endothermic heat as a reactant allows us to visualize the direction of shift with each one of these stresses. Let's consider the following example, and I pulled this from your a practice test, the actual multiple choice test. It says 2 POCl3s are in equilibrium with 2 PCl3s and an oxygen. Calculate the following delta H from this reaction. These are called heats of formation. The delta H of the reaction is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of reactants. Products minus reactants, an old formula from our thermodynamic chapter. The heat of formation of PCl3 is given to us as negative 288.7 kilojoules. And from our balanced equation, I see that there's 2 moles worth. The relative, or the heat of formation of oxygen, any element in its natural state, is 0. I wrote oxygen there, is 0. So the sum of my products, the 2 coming from the 2 moles of PCl3 plus 0. There's the products minus the reactant. There's 2 moles of POCl3, which is given to us at a value of negative 542.2. Let's sum the products. 2 times negative 288.7 is negative 577.4 plus a 0 minus 2 times negative 542.2 . That gives us a value of negative 1084.4. Let's subtract these. Negative 577.4 minus a negative 1084.4, and we get a reaction value of negative 1661.8 kilojoules. 2 times negative 288.7 minus 2 times negative 542.2. I thought maybe I hit that wrong. That's why I hit it twice. Is positive 507 kilojoules. I figured right here is where I made my mistake. This reaction came out with a positive value. So this reaction ends up to be endothermic. If it's endothermic, I like to think of the heat content is right up here as a reactant. 507 kilojoules of energy have to be placed into the reaction to force it to occur. Endothermic. Think of the heat as a reactant. If we increase or decrease, what will happen to their equilibrium constant if we increase or decrease with the rise of temperature? So what's going to happen to the K if we increase or decrease? All right, so here's what we're saying. Let's see if I can explain this clearly. I have this particular stress. I'm going to increase the temperature. As an increase in temperature, we know that the reaction will shift to the right to favor the product side. And when we have the equilibrium shifting to the right, making more product, that makes the K get larger. We favor product, making the equilibrium constant larger. The smaller the equilibrium constant, the more we favor the reactants. The higher, the larger, the bigger magnitude of the value favors the products. So by heating this up as an endothermic reaction, the equilibrium constant will get bigger because more product will be made. Let's put this to use with today's lab. I'm going to talk through briefly about each one of the Le Chatelier equilibriums that you'll be studying. Now I have my lab book open to page 19. This is where you see part A in terms of the data table page. In the front of your actual lab notebook, the notebook with the graph paper in the back. So on page 19 it says part A, we're going to be studying the methyl violet acid-base indicator. Now HMV will be the molecular form of our indicator, the protonated methyl violet. So with the hydrogen attached to the methyl violet, we'll see it yellow. When the proton dissociates from the methyl violet, we form aqueous ions. We'll notice that the methyl violet then is purple. And there is an ion in common when water dissociates. When water is placed in, auto-ionization of water forms hydrogen ion and hydroxide ion. What we're being asked to do in this particular series is to just keep adding a chemical, a stress, and watching what happens. And you know what side of the arrow you're on. If it's yellow, you're on the left side, and if it's purple, you know you're on the right side. So what I want you to do under the part A where it says water, you're going to write this equation out. HMV aqueous in dynamic equilibrium with H plus and MV negative. Do it the same under acid. Rewrite the entire equation again, and under the base, you write it exactly like this for a third time. Alrighty. Now, in the directions, as you're reading through your procedure part for part A, it says you're going to place a little bit of this methyl violet indicator into 3 different test tubes that contain water. So right off the bat, one of the first observations is, when you place the methyl violet in water, is this in yellow or is it purple? The color will be recorded at the top of the page right there where it says color of methyl violet in water. And then you'll know what side of the arrow you're on because the color will indicate. Now I just want to forecast a little bit. What ion do you see in common between the methyl violet and the water dynamic equilibrium? Well, of course, I see that proton, the H plus. If I place methyl violet in water, it's detecting the hydrogen ion in water, and you can predict what color you'll see. Just kind of common sense there. I would imagine when you place methyl violet into water, you'll see it purple, and you'll verify that because this is the ion that it's detecting. But now let's add acid. Just kind of talk through it. It says, into one of the test tubes, add a little bit of acid, which is HCl. I believe they have you adding 6 molar HCl. So what is that doing to our equilibrium? Well, notice the acid, HCl, has an ion in common with the indicator. The stress is adding hydrogen ion. If you add hydrogen ion, Le Chatelier says, we're going to counteract that, and you should see the color shift to yellow. Verify that with your observations. And if you add base to this system, what we're asked to do is use these arrow notations. Adding a base consumes the acid ion. Remember that chemistry would say H and OH react to make water. So if I add OH, I'm using up the hydrogen. Le Chatelier says if I consume it, I want to make more, you'll see it shift back to purple. So this is kind of the idea for the first part A. Test out the indicator. It's called methyl violet. You'll do so into one test tube by adding water, then add acid, then add base. And you can sit there all day long and add acid, add base, and see the colors go back and forth, back and forth. Acid-base indicator for part A. Let's turn the page and I'll talk about part B, the KSP of a solid. So our observed reaction is the dissociation of an insoluble solid called lead-2 chloride. If you looked at your solubility table, lead-2 chloride has a big insoluble symbol on it. Truth be told that it is slightly soluble, very, 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 very slightly soluble, and when it does so, it creates 2 aqueous ions, lead ion and the chloride ion. So this is the equilibrium that's being studied. However, we can't just add lead chloride to water because it won't dissolve. We have to coax it by making it and then kind of heating it up. So really what you're doing in step 1 of part B, you're adding 2 mils of a 0.3 molar lead nitrate. So 2 mils of 0.3 molar lead nitrate. And then it says add 1 mil of 0.3 molar HCl. Notice this is a double displacement. Lead goes to chloride, hydrogen goes to nitrate. So a double displacement reaction. This is our driving force. This is the precipitate lead chloride. And that's what we're studying, is that solid formation. So initially, a little squirt of lead nitrate, little squirt of hydrogen chloride, measure those volumes carefully, and you create a cloudy substance. This cloudy lead chloride forms. Then you're going to warm it up and observe what happens to the solid. Then you'll cool it down and observe what happens to the solid. Keep adding 1 mil water increments until no solid remains and record the volume used. Now let's talk through a little bit about what we just said. When I first put this reaction together, this is going to be a cloudy precipitate. When you warm it up, it disappears. Now remember, you're going to know what side of the arrow you're on, because if the solid is there, it's cloudy, and if the aqueous ions are present, it's clear. A clear solution like tap water. You don't see any chunky floaty solid particles. Now in the last one, letter A, you knew what side of the arrow you were on because you could see blue or yellow or purple yellow, whatever it might have been. Here you're going to look at cloudy to know you're on the solid side, or clear to let you know you're on the aqueous ion side. If we heat up this reaction, adding heat, add the heat, you're going to see the cloud disappear. Those aqueous ion side will be favored. If you cool it down, you're removing heat, you'll see those aqueous, like the solid cloudy particles, reappear. So right in this section where you're warming and cooling, you're verifying if the reaction is exo or endothermic. The last thing we're going to do is to actually calculate the equilibrium constant of this solid. Let's talk about what that will look like. So back to your, this is on page 20 now of your lab report, part B. So that top data table, it says, let's complete the chart for the KSP. Now remember, you measured 2 mils of a 3 molar lead 2 nitrate. How many moles is that? So how do I fill in that moles? Well, right now I would go 2 mils times 0.3 molar and I get 0.6. I'd report that as 0.6, but I'm going to report it as millimoles because I used a milliliter. Now you can report that as moles by going 0.002 liter times 0.3 molar, and you'll find that value as well. So it doesn't matter to me. It's just I like millimoles because they're easier to work with. So this value is 0.0006. So all I'm doing is using milliliters reported as millimoles. The other thing we did then was to measure 1 mil of a 0.3 molar HCl. So 1 mil times 0.3 molar gives me 0.3 millimoles. That's what I would place into that column. The volume, 2 mils for the lead nitrate, 1 mil for the HCl. The concentration, 0.3 for the lead nitrate, 0.3 for the HCl, and I multiply those by each other and I get millimoles, 0.6 and 0.3 respectively. Now the equilibrium concentration needs the value of water. How many milliliters of water did you add to get all the ions to disappear? Now, I don't know what it will be. Let me just make up a number and say it was 5 mils. I don't know, but I'm going to write that volume down. I'm just going to say, let's say it's 5 mils. It might be 20, it might be 3. You're going to have to find that out in the lab. How will you find the very last row of equilibrium concentration? Well, it's just a dilution problem, MV equal MV. Let's say you take that 0.6 millimoles that you found for the lead nitrate, and what would the new combined volume be? We had 2 mils of lead nitrate, we had 1 mil of HCl, and now I added 5 mils of water, so the new combined volume, 5, 6, 7, 8 mils. There's my new molarity for the very last line. The equilibrium concentration is the new molarity. The 0.6 millimoles divided by 8 mils gives me 0.075 molar units for the lead nitrate. Now remember, we found 0.3 millimoles of HCl in the new combined volume of 8 mils. So millimoles divided by milliliters gives me 0.0375 molar units. The only thing that's going to vary is this. You have to find that experimentally. Now, what are we supposed to do with that? How do we calculate the KSP? Remember our study for this equilibrium. Lead 2 chloride is in dynamic equilibrium with lead ion and 2 chloride ions. This is a pure solid. It drops out of our equilibrium expression. So the equilibrium for this soluble product, SP is for a solubility product, it's the study of salt dissolving, would be expressed by the concentration of the lead ion times the concentration of the chloride ion squared due to its coefficient. Well, where are these sources? The lead comes from right here. The lead nitrate is 0.075. The HCl gives me the chloride ion concentration. It's the source of chloride, so it ends up to be 0.0375 squared once we place that into there. And you'll just calculate out and find a constant, KSP. The concentration of the lead ion, the concentration of the chloride ion squared gives us the KSP for this equation. And then you're asked, is it endo or exothermic? And remember, that's based on this observation. Warming it up, you'll see the ions form. Warming it up, the solid cloudy particles disappear into solution. And when you cool it down, the solid starts to fall out of solution, knowing that we shifted back left. That's an endothermic reaction. Let's talk about part C. Oops, I already wrote this part out, didn't I? The expression for the KSP, you're asked to write that in your lab notebook. Remember that it was the aqueous ion of lead times the aqueous ion of chloride, but that needs to be squared. And we found out how to calculate those. Part C relates to complex ions. Complex ions of cobalt. Now, when I look at your e-text, your actual procedure for Part C, complex ions, do you notice that your book, the actual e-text photocopy I uploaded into Canvas, is missing a charge for the pink cobalt ion? When a complex ion of cobalt is hydrated, it carries a +2 charge. When a cobalt chloride complex is not hydrated, it is blue in color and carries a -2 charge. Notice if the water is attached to the cobalt, it's pink. If the chloride is attached to the cobalt and the water is not, then it's blue. Now this reaction has you start by taking out cobalt chloride that is hydrated. There's 6 water molecules on it, so you actually start by taking out CO, Cl2, 6 waters. This would be called cobalt 2 chloride hexahydrate. And you're going to add HCl. And that's 12 molar, so be very careful under the fume hood for that. Add a mil of HCl and observe the resulting color. So when you added HCl, you're actually creating this equilibrium that you're studying. So the very first, when you add HCl, is it pink or is it blue? And that will let you know what side of the arrow you're on. Now let's think about that. If you're adding HCl, what's the ion in common? The ion in common is the Cl. You're going to be creating a stress of adding more chloride. If you add water, in the next test tube it says add a little water. Well, here's the water. This is the stress that you're creating on this equilibrium. What will the system do? Will it shift to pink or stay blue? If you heat the test tube, now this will let you know if it's endo or exothermic. If it's endothermic and you heat it, it will shift blue. If it's exothermic and you heat it, it will shift pink. So seeing the color lets you know if it's endo or exothermic. Same thing with cooling the tube. If you cool the tube and it's endo, it'll turn pink. If you cool the tube and it's exo, it'll turn back to blue. So this is the process of figuring out the stresses on these complex ions. This one is nice, just like part A. The colors are how you know what side of the arrow you're on. Remember in part B, you know what side of the arrow you're on by looking to see if it's cloudy or clear. One more part, and that's part D, dissolving some solids. We're going to take a look at part D. First of all, it says go get some zinc nitrate, ZnNO3 taken twice, and you're going to drop in some sodium hydroxide into a test tube. You'll do this 3 separate times into 3 separate test tubes. Now look at the pattern of change. Double displacement, you form zinc hydroxide and sodium nitrate. So the first step of your procedure is to actually create the solid that we're studying. Very similar to the part B, we had to create lead chloride, because if you dissolve lead chloride in water, it just sits there and doesn't dissolve. Same thing for zinc hydroxide. It's generally insoluble, so you have to create it and get some of it in solution. Then it goes on to say add more 6 molar NaOH. So that first step is just making the zinc hydroxide. Step 1, into 3 separate tubes, there's your recipe. 1 ml zinc nitrate, 1 drop sodium hydroxide, and observe the solid formation. It will come out cloudy at this point. Next thing you do to a separate test tube, one of the three test tubes you just made, you're going to add sodium hydroxide. Add it drop by drop until you see something. And remember, the equilibrium we're studying contains a hydroxide ion. By adding more zinc hydroxide, you're actually going to consume the zinc. And that makes sense because we're going to shift back this way, and if we shift this way, the zinc gets consumed. You should see it go back to more solid. If you add acid, you're decreasing the amount of hydroxide, and therefore you can predict that the solution will become clear. And adding ammonia, again, look at this equation. Adding ammonia consumes the zinc. If you consume the zinc, you can predict what will happen according to Le Chatelier's principle. So this one, you have to make the solid and then stress that equilibrium out by adding different reagents, but you'll know what side of the arrow you're on. Either it's cloudy or it's clear based on left or right of the reaction. I'd like you to cross out the magnesium hydroxide. It's exactly the same as zinc hydroxide. It's not worth doing to see this exact same result. So I'm going to ask you to cross out doing magnesium hydroxide, and that means you're going to eliminate page 22 from your lab report. I hope you found this pre-lab talk helpful, and good luck with your lab today.